Okay, so it is now 10:15, so we're going to get started here. Um, this is Mr. John DeGood. Um, John DeGood is a senior lecturer in the Department of Computer Science at TCNJ. He worked 42 years in research and new product development at Hewlett-Packard, the David Sarnoff Research Center, and Lockheed Martin Advanced Technology Laboratories. He's a board member and past chair of the Princeton Joint Professional Chapters of ACM and IEEE Computer Society. He holds an extra class amateur radio license with call sign NU3E. His interests include antenna modeling, digital communication modes, and portable operation. So with that, John, feel free to get started.
Thank you, Alexander. So the bio gives you a little bit of the stage of why I might be interested in this. So I have not worked in industry with LoRa, but I was fascinated when I saw the technology announced a few years ago, and it fit nicely in with my amateur radio interest. I've been a ham since college, since back in the early 70s. So this is actually my 50th anniversary of having a ham license this year. And it's a very similar idea of having low power signals that propagate long distances. And while LoRa isn't using the ionosphere and going around the globe, it does propagate for a long distance with a very small amount of power. So let me go ahead and start with the slides. So the title that I chose for this was LoRa Long Range Unlicensed Wireless Networking for the Internet of Things. So I wanted to begin by talking a little bit about what the Internet of Things is, in case you're not familiar with that concept. It's a pretty common term nowadays, but I thought it was interesting when I looked into where the term came from. So it's often felt credited with being the first device other than a computer that was connected to the internet was back in 1982. And some people, I think they were students at Carnegie Mellon, connected their Coca-Cola machine up to the internet. And I remember reading about it back in the early 1980s that this was, kind of a big deal. Nobody had really thought about the internet was new at the time, and this was just kind of a crazy idea to put a Coca-Cola machine on the internet. And so people started talking about, internet connected toasters, and they were making all these disparaging remarks. But as time evolved, that kind of thing became true, and there have been internet connected toasters that have been sold. So the term itself, Internet of Things, is credited with a guy who was at the time at Procter & Gamble and later went to MIT, and he viewed it as some way to connect RFID tags to the internet. And he was thinking that that would be the key to an Internet of Things, was we'd be able to track the things as they moved around. But it's much broader than that today. So this is the definition that I like. And it's what time were there more things connected to the internet than people? And that Cisco estimates that was something between 2008 and 2009. And the ratio has just continued to grow in the interim. So here's a little chart showing that around that time, something around 2008 or 9, it's different estimates put it at a slightly different year, where things exceeded people on the internet. And by 2020, it was, nobody knows the exact number, but the best guess is there was something on the order of 50 billion devices attached to the internet versus 7 billion people. And another way of looking at it is the growth. It's been something that looks like an exponential curve as we just attach more and more devices to the internet. And I guess an important point on this chart to point out also is so compound annual growth rate from 2014 to 2020 in this part of the curve was about 23%, and increasingly it's industrial kinds of things rather than smartphones and other consumer devices. Okay, so here's an example of an Internet of Thing device that I built. So what I have here is a Geiger counter kit that I purchased from a individual in Israel who was selling these on the internet. So I bought this little kit, and so this is the Geiger counter that I assembled. It was just a board and a sack of parts. And then this is a Geiger Muller tube that I ordered from an individual on eBay in the Ukraine. There's a lot of these Soviet era Geiger Muller tubes floating around that are relatively cheap, that I don't know how they fell into individual hands after the collapse of the Soviet Union, but you can buy them on eBay for just a few bucks each. And then I have a USB power bank that powers the thing. And I hacked the software that came in this kit to interface to a GPS module. So this is a standard, one of the major suppliers of modular GPS devices is a company called U-Blocks or Microblocks. I'm not sure how they pronounce it. And they have a Neo family. Unfortunately, when I took this picture, I had it in this box. I have it in the box so it doesn't short out against anything, because the Geiger tube is running around 400 volts. And that would not be good for my electronics here if the 400 volts shorted to the rest, to the low voltage components. But this little GPS talks to the Geiger counter, and it is used for two purposes. I get a precision timestamp out of the GPS. And the second thing is that it tells me the position. And so I put this on my passenger car seat and drive around with it. And every once a minute, I have it programmed to upload the radiation reading from the last minute up to the cloud, up to the internet, to a server I have in the cloud. And then I can plot versus the map what the radiation reading was. And in case you're curious, background radiation is pretty much constant in this area. The only place that you might see an increase is if you park in a hospital parking lot and happen to have somebody come out who had just had some sort of, who just swallowed some radioisotope for imaging. And some of those emit enough gamma rays that you can actually detect them with a Geiger tube like this, even 10 or 20 feet away from you as they walk. And so anyway, this was kind of fun. Okay, another Internet of Things. I've had this running for close to 10 years. So one of my hobbies is I teach yoga classes, and one of the styles I teach is hot yoga. So in two of the studios where I teach, I built little Internet of Things devices. I built them in Chinese food takeout containers and hung them on the wall in the studios. And then every night at midnight, they send these graphs to me and to the owners of the studios. And so this was a particularly hot summer day a couple of years ago. And so the green chart is the temperature. You can see it even at the low point, it was still up in the high 80s. It didn't cool off very much that night. And then the red is the calculated heat index in the studio. From the peaks and valleys come from different classes being offered, and this basically the perspiration of the people who are doing the hot yoga practice. So it gets really steamy in there. So you can similarly see the peaks in the relative humidity, and then the barometric pressure comes out of the sensor that I use. So I just plot it for fun. It's not really useful for this application. So that's a little bit about Internet of Things. So the main focus of this talk is about a radio technology called LoRa. which stands for long range. So the main players in this technology are a company called Semtech, which holds the patent on the modulation, the signal for this technology. And there's a industry consortium, I guess I would call it, called the LoRa Alliance, that works with Semtech and various industry players to try to popularize the use of this radio technology. And then on top of the radio technology is a protocol that comes out of LoRa Alliance called LoRaWAN, which is connecting these long-range radio devices to the internet to allow the connectivity of the endpoint devices to go up to the cloud and be processed at servers in the internet. And then the Things Network is an example that I'll talk about a little bit later. And it's a crowdsourced implementation of LoRaWAN. So the idea here is that people will set up gateways for these devices and make them publicly available. And so that your friends and neighbors then could deploy LoRa and have a way of getting this data up into the internet. So people who want to share the infrastructure that they provided for free. And there are also private deployments as well. This one I found interesting as a hobbyist because it's open to anyone, and whereas most of the private ones are not. So what do I mean by long range? So the record, the so-called record oops, let me go back one here. The so-called record for LoRa is 832 kilometers, which is 517 miles. This is the first time we've talked about power. So this is a 25 milliwatt radio signal, so really low power. And this record was formed with a high altitude balloon. So they got this kind of distance by sending the LoRa sensor. This was just an endpoint device up in a balloon to 38 kilometers before the balloon burst. And it was picked up by just an ordinary LoRa gateway. So nothing special, no high gain antenna. This was just a LoRa gateway that someone had deployed in Europe. And it was the device that picked up the signal from this ordinary LoRa sensor, which went up on a balloon. In more typical usage, though, the long range means something on the order of 1 to 10 kilometers, so just a few miles. So as a real world example, I took a little, one of my little LoRa nodes that I built up, and I literally hung it with a battery from the rearview mirror of my car. And then I stuck a gateway up on the bed in my second floor bedroom, and then took off driving and drove around my community. And I was with the antenna, my gateway and antenna being indoors and only just sitting in a second floor bedroom, I was getting on the order of 1 to 2 miles range using my little Internet of Things device at 25 milliwatts of power. So that's the more typical range. The higher you can get the antenna and the more in the clear, the longer the range is going to be. So, obviously we're not all going to be sending things up on high altitude balloons, but several kilometers is pretty typical. In a dense urban area, you're not going to get that far, of course. If you're in Manhattan, in downtown New York City, the range is going to probably be hundreds of meters because of all of the RF interference plus all of the physical buildings. Okay, we can go even further than that, though. So I find this humorous. I'm a little bit of a skeptic. I'm hoping they succeed. Their schedule has been slipping and slipping and slipping, but this was a Kickstarter project several years ago called Ambisat. And so what they did was they sold to the participants in this Kickstarter these little boards, and the boards have a LoRa transceiver on them. And these people are trying to license a ride on a low Earth orbit rocket. And they want to shoot these things up into low Earth orbit. The people who buy these little boards, they have an accompanying little chip of a solar cell that you can attach to them. And then supposedly, as these boards orbit the Earth, the LoRa gateways on Earth will be able to pick up their signals. I'm a skeptic largely because of the reality of the radio bands. So different nations license the radio spectrums differently. And so as this thing's orbiting around the world, they've been running into a lot of regulatory issues because because different countries have they use different frequencies, they have different restrictions on power levels and duty cycles and all sorts of different parameters. And so I'm a little bit skeptical that they're ever going to be able to legally shoot these things up and have them sending out signals as they go around the Earth. But we'll see. Their current estimate now is late 2021, and I'll be watching them. So where does LoRa fit in? So this is from the LoRa Alliance, and it's a little optimistic. So if I was drawing this blue oval, I would not have it as tall as it is. So LoRa is best suited for really low bandwidth applications when you don't have a lot of data to send. So I'm really skeptical about overlapping it with things like Wi-Fi and low energy Bluetooth and cellular. If it does overlap, it's just barely with those. The range, so definitely longer than Wi-Fi or Bluetooth. And cellular, again, we know that cellular is ubiquitous, but it's ubiquitous because we're talking to cell towers. So realistically, the distance between a LoRa device and a LoRa gateway could be longer than the distance between a cell phone and a cell tower. So I will give them that for a individual link, the LoRa can probably go further than the typical cell signal. So what makes LoRa work? So I mentioned before this company called Semtech that holds the patent, and the patent, I put the patent number down here at the bottom of this slide. So they have several chips that Semtech sells, and the modulation format is unique. That's why they got a patent on it. So it's a spread spectrum chirp that is frequency modulated. And the IP that's in this patent, they came up with a novel way to generate this chirp using something called a fractional in phase lock loop, which is way beyond the scope of what I want to go into in this talk. But I did want to show this picture, which I found, which is really nice to give you some idea of what it looks like on the air. So this is the chirp. It's called a constant ramp chirp, and it has a relatively long preamble. And so before the data starts going, the chip comes alive and starts generating this bare chirp signal that the receiver can lock onto. And I highlighted here in bold that this is the kind of the key that makes this technology neat, is that you can take an inexpensive chip and put a cheap crystal on it, so it doesn't need a precision time base, and the receiver can lock onto this constant preamble and then decode the data successfully with these low-cost parts. And so it's really clever from a electrical engineering technology point of view. So the data rates, what can we do with this? So the data rates are adaptive. So the overall system will manage the data rate and to try to maximize the efficiency. So the data rate will go up and down, as will the amount of airtime that's being used, the duty cycle, with the quality of the signal. So if you're near to the gateway that you're connected to, or if there's not many other devices in the area such that you're reliably getting through, then the power will get sent. The power will be used then to send more bits per second, or the bits per second will be put into a different bandwidth to maximize the efficiency. So the data rate changes with time, which is kind of interesting. Cell systems do something similar with power control as well. So the baud rates are low. So something in the range of 300 bits per second up to a few tens of kilobits per second maximum. Usually it's more down toward the lower end of this range. So there's basically, there's several knobs that you can turn to change the data rate, the resultant data rate. And so one of the knobs is the channel, and the channels that are available out of the chip are relatively wide because this is spread spectrum. So 125, 250, or 500 kilohertz. And again, because of different nationalities having different regulatory requirements, depending on what region you're in and what frequencies you're using within that region, that's going to dictate which of these are available to you. So that's the bandwidth, the spreading factor, as well as the transmission power are up to the user. There's a limit on the transmission power also. So the lower you set it, obviously, the less battery you're going to use, but the range is going to be lower. So the data rate and spreading factor are affected by the bandwidth. So if you double the bandwidth, you can double the data rate at the expense of shortening your distance, because you're spreading your power over a wider range, or more bytes in a wider range. And then similarly, the spreading factor is how fast you're modulating the data onto the spread spectrum. And so I like the analogy that I got off of this Things Network website. They compare it to two people talking in a noisy place. So if you're far away from each other, you have to talk slow to get your communication across. But if you're right next to each other, you can talk faster and still be understood. So that's where the spreading factor comes in. And the adaptive data rate will automatically change these with time to try to optimize the connection. So LoRaWAN is the overall system of taking a LoRa connection between some end node and a gateway. So we haven't talked about possible applications yet. So pet tracking, smoke alarms, water meters, vending machines, trash containers. The idea here is some sort of a device that periodically needs to send data, but not very often. And because you can't send very much data, the data budget is very low in this, but the distance for a given amount of battery power is very long. So these devices connect to whatever gateway is nearest them. If there's more than one gateway near you, your signal will be picked up by each of the gateways. Then they use the internet to take the data from the gateways and put it up to a network server that's operated by someone. It's a publicly available protocol, so you could implement your own LoRaWAN server, or you could use, say, the publicly available Things Network server. So that brings the device in nodes data up to the server, And then you can have one or more applications that use that data. And the data is secured by the AES encryption. So from the end node to the application, there is encryption. This is a little more detailed picture. So the end node device is over here on the left. And so there's going to be some sort of an application running in the device. And then the LoRaWAN protocol, a hardware abstraction layer. SPI is serial peripheral interconnect. It's a hardware protocol that the Semtech chip typically uses to talk to a microcontroller. So then this is the Semtech chip. And so it's going to then it's going to be connected to an antenna, and that talks to another Semtech chip over in a gateway somewhere. So in the center here is our gateway. This picture is a little bit dated, or at least, or else it's a typo. I'm not sure which. I'm guessing it might be a typo. Whoever made this up may not have really understood things. The LoRa chip supports several protocols, one of which is a simpler protocol called FSK. And in general, LoRa isn't very often operated with that modulation. So I'm not sure why they put FSK on this slide, but I like the slide otherwise. So anyway, this chip is going to receive the signal from the sensor, again, connect to some sort of a microcontroller in the gateway. And so it gets forwarded up through an internet protocol stack and goes out on the internet, and then comes up to the LoRaWAN network server. And then from the LoRaWAN network server, it will go out and connect to some customer application, which also is sitting on the internet somewhere. So this is a picture off the Things Network site. And as I mentioned, this is the one that's crowdsourced. So a couple of the gateways here in the 478 bubble are mine in New Jersey that operate in my home. So in the Things Network, there's currently 17,500 gateways as of the time that I took this snapshot of their website earlier this week. LoRaWAN defines several different classes of endpoints. So the simplest one is called Class A, and it's what you would use for a simple sensor. So it's the lowest power. It is bidirectional. If you have a more demanding application where you need to have deterministic latency, then there's Class B, and then there's a Class C, which is even more demanding. The Class C is going to require that the device always be active, and in order to get the lowest latency, as a result, it's not going to be suitable for battery power. The Class B is a compromise in which it wakes up periodically, and so it's low enough power that it'll work for a lot of battery applications, but not all. The Class A, you can literally get years out of a battery with a properly implemented Class A sensor. Okay, the security I mentioned is uses AES, and there's a network level security between the end device and the network, and then there's also another layer of security between the application. So there's two encryptions that go on. There's two protocols. You can either have the device pre-authenticated, which is called activation by personalization, ABP. So they can basically bake the keys in on the production line. The more preferred one is the over-the-air activation, the OTAA. That's what I've used in my experiments. It's not much more complex, and it allows you to dynamically rekey the devices, so you can change the encryption keys on a regular basis. It's going to be more secure that way. Okay, so this is one of the more important slides in my presentation, is duty cycle. So this is the LoRa typically runs in unlicensed radio spectrum. And so the government puts restrictions, and different governments have different restrictions depending on where you live, for the use of this unregulated spectrum to make it more fair. And so in many cases, in many governments, a typical duty cycle is you can only use the frequency 1% of the time. So you need to, wherever you're going to deploy this, you need to check the local regulations. It's the FCC in the US, and that's going to be one bound. And then if you're using a network, whether it's a crowdsourced network like the Things network, or if it's a commercial network, they want to make it fair also. They don't want one person hogging the spectrum. So the Things network has fairly strict rules. So for the uplinks, you can use at most 30 seconds per day of airtime. So 30 seconds in 24 hours. But actually, uploading a typical reading is going to be a fraction of a second. So this would let you send several sensor packets per hour up to your cloud application. And it's even more strict on the downlink sending to the device. It's 10 messages per day per node. So if you're on a private network, you aren't restricted by these limits, but you still have to abide by the government limits on the usage of the RF spectrum. But if you're using the LoRaWAN, there's much more strict limits on the Things network, or basically any of the private networks you might subscribe to too. So where would you find a good use case for LoRaWAN? So if the distance needs to be relatively long, it can be kilometers, and low power, years on a battery, low cost, so less than $20 capital expenditure per node, and virtually no operating expenditure. Stick it out there, the battery will last 10 years, so the operating cost is essentially zero. But the bandwidth is really low. So this is data from Europe. So the range of bandwidth that you can get in Europe with the regulatory licensing is going to be between 250 and 11,000 bits per second. And so if you have a lot of data, this is not the protocol for you, but if you just want to send sensor readings periodically, it's great. Coverage everywhere. So it's a public spec. You create your own network. Just plug a gateway in, connect it to the internet, and you're up on LoRaWAN. And so you can build the thing yourself, install as many gateways as you want to cover as big an area as you want. You're not restricted to a network provider, and it's secure. So what is definitely not suitable for LoRaWAN? It's not real time. You can only send a little bit of data, and at most every couple minutes. You're not going to do a phone call over this. If you want to control lights in your house, there's better suited protocols like Zigbee and Bluetooth that are made for that. And if you want to do even more bandwidth, photos, Netflix, etc., that's what Wi-Fi is for. So if this sounds like fun, how do you get started? So I picked the endpoint developer kit that I've been using. It's made by a Chinese company called Heltech, and this is their version 2 product of the device. So I guess before I point to the picture, let me go over some of the specs. So it has a dual core 32-bit processor called the ESP32, and it also contains an ultra low power core. So you can put it to sleep and have it periodically wake up. So when it's asleep, only this little ultra low power core is running just to decide when to wake up next, basically. So it has one of the little Semtech LoRa chips on it, has a micro USB interface here. And there's basically just two chips on this device. There's the ESP32 underneath this display. And then there's another chip, which is a USB, it's the CP2102 USB to serial port chip that lets the processor here talk to a host computer over USB for development. But the powerful thing on this is the ESP32, because the LoRa comes out of the Semtech chip, but the ESP32 has both Wi-Fi and Bluetooth. So this little board has 3 radios on it. The LoRa is over the longer antenna. This is just a little helical antenna. It's just a little coiled wire inside of this black plastic tube. And then this little coil on the board that you can see that I'm pointing to is used for the Wi-Fi antenna. And then there's a little trace on the board that's used for the Bluetooth antenna. And this little board has a dot matrix organic LED display, 128 by 64, which is really useful when you're debugging, or even for some applications that might be all the user interface you need. And it's easy to program. You can use the Arduino development environment. So how much does all of this cost? I pulled this off of Amazon yesterday. So the current price of these boards, quantity 1 is 21 bucks. So it doesn't cost much to get started with this. And so all you need is this, and then you plug this in with a USB cable to a PC or laptop, and the USB supplies the power and makes the data connection, and you're up and running. So 21 bucks is all it costs to do an end node. The development, I'm not going to spend any time on this. I just put one slide up. The Arduino IDE, there was, it has been extended to work with many other hardware platforms beyond the Arduino hardware itself. And so you can do ESP32 and the LoRa development in using the Arduino IDE. So it's got a nice integrated development environment, graphical editor, and all you do is this little arrow that I'm pointing to on the screen. You just click it and it will compile your code and then download it and burn the flash on the board. And you're in a few seconds, your code is up and running on the little board that I showed on the previous slide. Okay, you also need a gateway. So if there is already a gateway near you that's public, like the Things Network, then you don't need a gateway. If there isn't one near you, which is probably going to be the case, this is not deployed in a huge area in the US yet. This is one of the cheapest ways you can do it. So I have one of these in my house. This is the Things Network. The crowdsourced network sells these. They're $89 retail, and you can't see in the picture, but on the back is a power prong. So you can just plug this into a wall outlet, and then you initially connect to it via Wi-Fi. And so it looks like a Wi-Fi hotpoint initially, and then you program into it your real Wi-Fi hotpoint, and then it reboots and comes up as a Wi-Fi client instead of as a Wi-Fi server, as a Wi-Fi gateway. And so it will then receive LoRa radio signals and send them via Wi-Fi to your Wi-Fi access point, which then goes out onto the internet. And it also on the bottom has a USB connector. So if you're not, if powering it from the AC line is not convenient, you can plug a USB cable into it and power it via USB. And then I also have one of these that is on loan to me from the college that they had been doing some work with it. And this is a commercial gateway. It costs about $250. You can also buy this in an external version in a weatherproof container that you can mount on a pole or a tower or on your chimney or whatever to get longer range. And so it has the LoRa antenna, then has a pair of antennas for Wi-Fi, and then it also has the option of putting a cellular radio in it to do the backhaul to the internet over cellular if you're in an area, if you want to mount this somewhere where you don't have an internet connection otherwise. Okay, other contenders for Internet of Things. Before I do that, let me switch screens here. And I just wanted to show you this graphic because it's kind of cute. So the LoRa people put this out, and it's an infographic. I'm just going to kind of slowly scroll, but it shows some of the places where LoRa has been displayed. So in Asia and Africa, they've got tracking sensors on endangered species. So they've got, sensors on black rhinos so they can track their movements. They have LoRa devices that skiers can wear. So ski students, in case they get in an avalanche or get lost or whatever, they can track them via LoRa. There are urban noise sensors in Canada that have been displayed. They're using them to track dementia patients. It's some locations in the US, disaster relief. I guess you can read these as we go. They're used in agriculture, on islands, in campuses, water systems, food safety, tracking luggage through airports, smart bikes that get monitored for rental bikes in China, on and on and on. They're used a lot in workplaces. So the indoor gateways that I have in my house, the two that I showed on the slide recently, it's reasonable to have indoor deployments in a factory or in a workplace to track things like occupancy, energy use, parking, etc. And then there is a commercial startup that is going to be, at least if they get their funding and get it off the ground, is going to have a fleet of satellites that will be able to act as orbiting gateways and receive the signals from devices, so that if you don't want to have physical gateways on Earth, your device can periodically send signals via this LoRa gateway in space. Okay, to finish up, I want to show you, let me get back to my original slides, is other contenders. What's the competition for LoRa? So Sigfox is the one that they were a real pioneer in this idea of a long-range, low-speed network for Internet of Things. So it came out of France, and their vision, their business model, it's worked better in Europe than it's worked in the US. So they originally were planning on building a US-wide network. And over time, they came to realize that the US is a lot bigger than Europe, and it's a lot of territory to cover. And so then they tried to pivot and license their protocol to people like T-Mobile and Verizon, and the large telecoms viewed them as competition. They wanted to do it themselves. So they've kind of retrenched on the US. And so now Sigfox is focusing on small, discrete deployments rather than trying to blanket the whole country. But it uses a simpler protocol, just either a phase shift keying or frequency shift keying. And instead of being spread spectrum over hundreds of kilohertz, this is ultra narrowband. So they put their signal in a very tiny sliver of spectrum. And because they do that, there are some limitations. Because of the intensity of that signal in the narrow bandwidth is a lot stronger than the spread spectrum signal, which spreads it over a very wide bandwidth. They have some more severe restrictions on how much data that they can send per unit time. Okay, so that's Sigfox. The cellular providers have their own, they're trying to get into this business. They see dollar signs. They see billions of devices that need data connectivity. And so, that's potentially billions and billions of dollars if they can get those devices to pay them to carry their signals. So the slowest, the one that's closest in performance to LoRa is something called NB-IoT, narrowband for Internet of Things. So the peak data rate is in the same ballpark as LoRa, 26 kilobits. Downlink and the base uplink bandwidth is 16.9 kilobits per second, or a little bit faster if you use a multi-tone modulation. Has big latencies, 1.6 to 10 seconds latencies when you want to send something to when you can actually get it out. But this is licensed spectrum. This is running on top of the standard cellular networks. And so you don't have competition from other signals. And this has been deployed, this narrowband Internet of Things. They're sending it in a little sliver of LTE bandwidth, and they typically have been deploying it in between the LTE bands. There's these little gaps called guard bands between the LTE bands, and so they've been sticking NB-IoT in those guard bands. So if you have an application that needs frequent communication, more frequent than what you can get with the LoRa, then NB-IoT might be for you, but you're going to have to pay for it. You're running on licensed spectrum, and the cellular companies are going to charge you to connect over that network. So the next step up from this is called LTE-M, which is an alias for LTE Cat M1. This is a megabit per second kind of rate with much better latency of just tens of milliseconds. And it's got enough bandwidth that it can support voice over the network as well. But because it's more bandwidth, it costs more. So an LTE-M connection from the phone company is going to cost you more per month. And the bandwidth is wide enough that it currently doesn't fit in these guard bands where these little slivers of spectrum where NB-IoT is deployed. Okay, the last one I wanted to mention, which you may or may not have read about, is something called Amazon Sidewalk. And so Amazon is an interesting company. They came up with this idea of connecting Internet of Things devices through their existing infrastructure. So existing Amazon Echo devices, Ring doorbells, Ring cameras have built-in, these are all internet connected devices to start with. They have radios already built in. Your Amazon Echo has Bluetooth built in. The Ring doorbells and cameras have Wi-Fi, or they both have Wi-Fi as well as Bluetooth. The Ring doorbells and cameras additionally have LoRa chips in them. And Amazon's vision is they're going to be using this in a lot of future devices. So the first one that we know about comes from the Tile Tracker company, and they have a pet collar called Fetch that works with this system. And the idea is if your dog or cat has this pet collar on and wanders off, you can find them. because if they're anywhere near a home that has an existing Amazon Echo device or a Ring doorbell or a Ring camera, it will pick up the signal from the pet collar, and you'll be able to figure out where your pet wandered off to. But it's controversial because Amazon is deploying this in these customer-owned devices, Echoes and Ring devices, and they're using customer bandwidth to connect these devices to the internet. And so your neighbor's dog or cat the data from their pet collar is being picked up and using your internet bandwidth to be tracked if they wander in range of your house. And so it's been controversial. So Amazon had to put an option when you configure your Echo or Ring, whether you opt into allowing the Sidewalk to use your internet bandwidth. But this is a way of getting widespread deployment and not having to pay bucks to the cell companies to carry your signal. It gets picked up. Again, this is sort of a variation on the crowdsourced theme, but it's kind of a non-voluntary, in a way, crowdsourced, because your people who have bought Amazon devices willingly or unwillingly participate in this network of gateways for the Amazon Sidewalk protocol. So for things within the house, Bluetooth Low Energy can talk to the Amazon Echo devices, the existing ones, and then the LoRa requires currently the Ring devices in order to make that connection. Okay, so I think I've talked long enough. Let me stop sharing my slides and ask for questions.
Yes, we have a few minutes for questions here. If anyone has any questions, you're welcome to unmute yourself and ask them, or put them in the chat. And then we'll be taking a 10-minute recess for you to change sessions or whichever you like.
Yeah, I will be sharing these slides, so I will give them to TCF, and they will post them on the TCF website eventually in the not too distant future. So that's one question in the chat. And I have a direct message here, and let me go ahead and read it. And someone says that they want to use LoRa for operating relays to change their wire antenna array geometry. So probably a ham radio operator. So which LoRa Class A hardware operates with lowest power, and what about sleep mode and wake up? So the ESP32 processor, the little $21 board that I showed you, could be used for that application. If you want to have the lowest power, then you would want to disable the display on that board. The board also has some other circuitry in it that you might want to display. So there are other development boards that are less feature rich, that if you want to get the lowest possible power, that might be a better choice than the Heltec board that I chose. But again, there's probably not an off-the-shelf solution that directly does what you want, but there are definitely all the pieces there. If you're a experimenter, that you can do this yourself. There's a LoRaWAN stack that is open source that you can download from GitHub, and you can put that together with open source Semtech drivers. And so all of the core software that you would need to build this is open source, and one of these little development boards would probably might be low enough power for you. If you want the absolute lowest power, you might want to do your own custom board with a processor like the ESP32 or something else that you can put into a deep sleep mode between wake-ups. Okay, any other questions? Feel free to unmute. You don't have to use the chat. Okay, Rob from the chat says, what's the advantage of Zigbee or Bluetooth Low Energy over LoRa for home automation? And is it off-the-shelf devices? Yeah, it's probably off-the-shelf devices more than anything else. Also, the range advantage of LoRa is not really necessary if all you're trying to do is toggle light switches and appliances within your home. So if your range is tens of meters, then you don't need LoRa. Bluetooth Low Energy or Zigbee are probably going to be adequate.
If anyone else has any, sorry, go ahead.
Yeah, I'm just going to say what you were going to say. Does anybody else have anything? My email, I'll put it in the chat, is if you want to send me email, you can use my college address. So it's dgoodj@tcnj.edu. It was on the cover slide. So once the slides are posted, you'll have it there. So if you think of a question afterwards, you can feel free to contact me. I'm happy to help as long as you use some restraint. I won't answer multiple questions per day from the same person, but within reason, I will try to be helpful.
Well, we're perfectly on time. That's just great. Fabulous.
So if there's no other questions, thank you, Mr. DeGood, for your presentation. We will be taking about 9 minutes from now to about 11:20. The next presentation will start. Feel free to stick around for that one, or do as you please.
Okay. Thanks, Karen. Thanks, Alexander.
Thank you so much. Thank you so much, John.